Hi guys.
Hello.
Okay, so in this tutorial we will be covering a couple of exercises from exercise 1.7, 1.8, 2.1 and 2.2. So it's a lot to cover, but we will try to cover as much examples as possible. Another thing is the notes that I take during the tutorial, I have uploaded it on the Moodle. So you will be able to find the notes under the tutorial information. So if any of you needs the notes, you can find it there. And regarding the tutorial, so the videos for the tutorials can be found on Microsoft Streams. Okay, so let's start with exercise 1.7. Okay. Okay, is everyone able to see the screen?
Yes.
Okay. So we have the first question from exercise 1.7. It's on page 95. So we have to use a direct proof to show that the sum of two odd integers is even. So first what we will do is we will suppose what those two integers are. So let n be one of the integers, and then we can say that n is 2k plus 1, and then we can say another integer m equals to let's say 2l plus 1. Okay, so they are our two integers. So we are saying that the sum of two integers, so n plus m will be equal to 2k plus 1 plus 2l plus 1. We can simplify to 2k plus 2l plus 2. Further, we can take the LCM k plus l plus 1. Okay. So with this, we know that this number here, this is actually an even number because it's a multiple of 2. Okay. So therefore, it is even because it's a multiple of 2. Okay. Okay. So any questions here? If no questions, let's move on to the next question. This is the question 5. So we have to prove that if this number and this number are even integers, so we assume that they are even. Where these ones are integers, then m plus p is even. What kind of proof did you use? Okay, so we can basically use here a direct proof. And how we can do that? Because it's really straightforward. So we suppose that m plus n and n plus p are even by the question, then m plus n equals to 2s for some integer, let's say s, and n plus p equals to 2t for some integer t. Okay, so we assume that let's say that this is equal to s and this is equals to t, 2t for some integer t. Okay, here. Okay, if we add this m plus p plus 2n equals to 2s plus 2t, right? So if we add them together, so it's like this. Okay, now subtracting 2n from both sides and factoring, we have m plus p equals to 2s plus m plus p, because here we have a plus p plus 2s 2n. So we subtract 2n from here, so this 2 get cancelled out, so we can remove them, and then we get 2s plus 2t minus 2n, right? So this is equals to here, right? This is equals to 2s plus t minus n. Okay, so m plus p equals 2 plus t minus n. Okay. Now, because we have written m plus p as 2 times as integer, we can conclude that m plus p is even. Okay, so basically what we did is, so we suppose, as in the question, that these are two even numbers, and then we said m plus n equals to 2s. So suppose we take some integer s, right? So if we multiply that integer by 2, right? So let's say if that integer is odd, so if we multiply that integer by 2, it becomes even, and if it's even, we multiply by 2, it's become even as well. So this is just to make sure that the number is even. Okay, and then we try to add these together, and then we factorize it, and then we said that because we were able to write this as 2 times as integer. So therefore we know that m plus p is even. Okay, any questions?
Miss, how do you know when to add or when to subtract if you want to prove something?
Well, it all depends on the kind of proof we are doing, right? So in this case, what we are trying to prove is that they are even integers, right? So we have to come up with some sort of a mechanism to make that kind of a proof, right? So this is one of the kind of proof, right? So this is direct proof. We can use different kinds of proof like contraposition or contradiction or different kinds of proof, depends on the way you think. Okay, so let's move forward to another question. Okay, so we have this question number 13 here. So we have to prove that x is irrational, then 1 over x is rational. Okay, so for this kind of proof, what we will be using is the contraposition proof to prove this statement. Okay, prove contraposition proof below. So if 1 over x were rational, then by definition, because if some number is a rational number, we can write it as p over q, right? So we assume that if this is rational, then by definition, 1 over x equals p over q, right? For some integers, let's say p and q are some integers. For some integers, p and q, and q must not be equal to 0. Okay, because if p is this q is 0, then it goes to infinity, and this is not a rational number then. Okay, so now because 1 over x cannot be 0, right? Because if it were, then we have the contradiction 1 equals to x, right? Because otherwise we will be able to say 1 over x one equals to x multiplied by 0, because if this is q equals to 0, so then we will be able to say that 1 is equals to x multiplied by 0, and if anything multiplies by 0, it becomes 0, right? And 1 is not equal to 0, right? So we know that p is not equal to 0. Now we have x equals to 1 divided by 1 over x, which is in terms of p and q, it will be 1 divided by p divided by q, p divided by q, and if we just flip the sides, Further simplify it becomes Q divided by P, right? So just by using the rules of arithmetics. So hence X can be written as the quotient of two integers with non-zero denominator. Therefore, X is rational. Okay. So basically what we did is, so if we have any number, so X, if we say that this is a rational number, then we can write it in the form of P over Q, right? So this is the definition of a rational number, and Q is not equals to 0. Okay, so Q is not equal to 0. So this is the definition of irrational. So just by using the definition and the proof of contraposition here, we prove that it's a rational number. Okay, let's move on to question number 19. So we have if n is an integer and n3 plus 5 is odd, then n is even. So we have to prove this statement. Now we have to prove them by using contraposition and contradiction. So we will prove it using contraposition. Okay. So in here we assume that n is odd, right? So n equals 2k plus 1. So we are adding 1 to make sure that this is odd, and then for some integer k, we just assume there's some integer. It doesn't matter, it can be odd or even, but by adding 1 it makes sure that it is an odd number. So then n cube plus 5 then n cube plus 5 equals to 2, right? So 2 times, and then k value, the value of k is 4k cube plus 6k square plus 3k plus 3. Okay, because n cube plus 5 is 2 times some integer.
Isn't that 8k cube?
I'm sorry?
Isn't that 8k cube at
8
the beginning?
here?
Yeah. 2 cube?
Yes, you're right. It's 8. Yeah, 2 cube is 8. Yeah, all right. Okay. So because n plus 5 is 2 times some integer, so therefore It is even. So this was proved by contraposition. Okay. Move on to the next question. So we have this proposition here. Okay. So if A and B are positive real numbers, then we have to prove this. So prove that P1 is true. So we know that the value of n is 1. What kind of proof did you use here, right? So we have to use, basically we will just plug in the value. So we will use the direct proof here, right? So here we have P of 1. So A plus B. So we have A plus B and to the power of 1, right? And then we are saying that this is greater than or equal to A to the power of 1, right? Which is basically equals to A itself, right? And then plus B to the power of 1, which is B itself, right? So now we know A plus B to the power of 1 is A plus B itself. And we say B is greater than or equals to A plus B. And then we know that A plus B equals to A plus B. So this is a direct proof. Okay, let's take the last question from this exercise. So we have to prove or disprove that if m plus n are integers such that m is equal to 1, then either m equals to 1 and n equals to 1, or else m equals to minus 1 and n equals to minus 1. So we have to prove or disprove this statement. So this is here a proposition, right? So we have to figure out what the truth value is. So we know that this proposition truth value is true. And how? So we can suppose that m is neither 1 nor minus 1 nor minus 1. Then we know that mn has a factor m larger than 1. Okay. On the other hand, so we know that mn equals to 1. If it's mn equals to 1, then and we know that 1 has no factor. We cannot factorize it, right? So because the only factor is of 1 is itself. Okay. So hence m equals to 1 or m equals to minus 1. Okay. So in the first case where n equals to 1, right? And both in the second case where n equals to minus 1, right? Because n equals to 1 over m. So therefore, this proposition is true. Okay. So what we did is, so we suppose that m here. So basically what we have to do is we have to prove or disprove such that mn equals to 1. So we have to prove or disprove thus mn equals to 1. Then if this is 1, then either m equals to 1, n equals to 1, or else this is this. Okay, so what we did is we suppose that m is neither 1 nor 1, then mn has a factor m that is larger than 1, right? And on the other hand, if mn equals to 1 and 1 has no factor, right? So hence m equals to 1 or m equals to minus 1. Okay. And then in the first case, when we had n equals to 1, and in the second case, we know that n equals to 1 over m. Okay, let's move on to the next exercise. We have exercise now 1.8. So let's take the first question from this exercise. So we have to prove that n squared plus 1 is greater than equals to 2n when n is a positive integer, and we have to prove that within this domain, right? So one way of doing this is taking all the elements from 1 until 4, right? And which is what we're going to do here. Okay, so we have the statement. We'll just plug in the values here for n. So 1, so we'll take 1 square plus 1 is greater than or equals to 2 to the power of 1, which is equals to, so here 1 squared 1 is, so 2 is equals to 2, which is true, right? So we prove it for when n equals to here 1. Likewise, we will do it for 2 square plus 1 is greater than equals to 2 square, right? And then it will be 5 is greater than or equals to 4. So this is also true. Likewise, we will do replace this.
Why is the second one true?
5 is greater than 4. That's why.
Oh, wait. Oh, okay.
Right. So here we will replace these values with n here, right? So we have from 1 until 4, right? So we'll keep replacing it, and then we will find the answer. Okay, and we'll find out for it's true for 1, 2, 3, and 4. So therefore, we will prove this whole proposition. Okay, let's move on to the next one. This is question number 5 here. So so we have two real numbers x and y, and then we are saying that the maximum of x and y plus minimum of this equals to x plus y, and then we have some hint here. So we will see. So if we have ax less than equals to y, So this is not an arrow sign. This is, here it is. X is equal to or less than y, then the maximum of x and y plus minimum of x and y equals to y plus x, which is equals to x plus y because of the loss we studied in the previous tutorial. Okay. Now if x is greater than equals to y, then max of x and y plus min of x and y equals to x plus y, right? Because these are the only two cases possible. So we know that the equality always hold. Okay. Any questions? Okay, if no questions, let's move to the question number 13. Okay, so in question number 13, we got to prove that there exists a pair of consecutive integers such that one of these integers is a perfect cube and the other is a perfect cube as well. So in this one question, this is a pretty simple and straightforward question. What we have to do is we just have to come up with some number, right? So in which one of that integer is a perfect square and the other is a perfect cube. So one example of that.
Sorry for interrupting. Where can I find this? Is it on Moodle? Like, yeah, are you going to upload this on Moodle?
Yes, I'm gonna upload this notes after the tutorial on Moodle, but for the previous ones, I have already uploaded them.
Oh, okay. Thank you.
Okay. Okay. So any other questions? Okay. So we have to find a number. Prove that so we have to find a pair of consecutive integers, right? So it's a pair. It's not one number. It's two number, and it has to be consecutive number. And one of that integer is a perfect square and the other is a perfect cube, right? So here we can say if we could take the number 8, right? So we know that 8 is a perfect cube, so it's a cube of 3, right? And then the consecutive number of 8 is 9, right? So we know that 9 equals to the perfect square of 2. So we prove it just by thinking of two numbers. Okay, let's move forward to question number 21. So in question number 21, so we have to show that if n is an odd integer, then there is a unique integer k such that n is the sum of k minus 2 and k plus c. Again, it's very much related to finding some number k. Okay, So we're asked to basically solve n equals to n equals to, let's just write here, n equals to, this is small n, right? So n equals to a minus 2 plus k plus 3. Okay, so n is the sum of k minus 2 and k plus 3. So if we solve this, right? So using this usual reversible rules of algebra, we will see that this if we solve this for k, so let's solve it here. So we have this n equals to k minus 2 plus k plus 3. So now we have k plus k, it's 2k, and minus 2 plus 3 is plus 1. And this is n. So let's solve this for k. So n minus 1 divided by 2 is the value for k in terms of n. So in other words, this is the one and only one value of k that makes our equation true, because n is odd, n minus 1 is even, so k is an integer, right? So here, so when we solve this here, so we will get our value of k, right? And then that's the only value of k which will make this statement true, this equation true. And we also know that this n here, right, it's odd number, odd, right? So if we subtract 1 from an odd number, it becomes even. Even divided by even is an even. So we know that this k is an integer, and that's an even integer. Even integer. Okay, any questions? Okay, if no questions, let's move forward. So we have this question number 33. Here we have to prove that there are no solutions in positive integers x and y to the equation x to the power 4 plus y to the power of 4. Okay. So because 625 is basically 5 to the power of 4. 5 to the power of 4 equals to 625. Okay, so we know that both x and y must be less than 5, right? So then x to the power of 4, then x to the power of 4, okay, x to the power of 4 here plus y to the power 4 is less than or equals to 4 to the power 4 plus 4 to the power 4. Basically 4 to the power 4 is 5 to the power 12 is less than 625. So we prove that there is no solution in positive integers x and y to this equation. Any questions?
Nope.
Okay, let's move on to the next question, next exercise. So the next exercise will be exercise 2.1. Okay, and so exercise 2, basically chapter 2 is about these sets. So this is going to be the first question of 2.1. Okay, so we have a statement in set notation form, and then we have to list the members of these sets. Okay, so let's take part number A. So basically here what we have to do is we have this x is a real number such that x squared equals to 1. So we have to list the numbers. So in order to list, we use this notation. So the only possible elements that covers this criteria are -1 and 1. So these are the members of this set. Okay, because I put -1 square equals to 1 and 1 square equals to 1. Other than this, no other number satisfies this condition. Okay. Let's take part number B. So part number B, we have two positive numbers less than 12. So we start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, less than 12. Okay, so we have to basically list all of them less than 12. Part number C, x is the square of an integer and x is less than 100. So here we will have to list all the squares of a number. So 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Okay, and that should cover all of the elements. Number D. So we have to find all the numbers such that x squared equals to 2. So we know that there is so if we take, let's say it's 0, so 0 square equals is not equals to 2, 1 square is not equals to 2, 2 square is not equals to 2. So therefore we know that there is no element that satisfies this criteria. So it's an empty set. In order to write the empty set, the notation for this empty set is this. So it means that there is nothing in the set. We'll put here empty set. Okay, any questions? Okay, no questions. Let's move forward. We have question number 9. So you have to determine in these the solutions of these sets is to a member of these sets or not. So if we take part A here, so x is an integer greater than 1, right? So 2 is greater than 1, so therefore we know that 2 is a member of this set, so therefore it's true, or you can say it as a yes, or okay, let's put it yes, because now we have is the square of an integer, right? So 2 is, as we saw earlier, that 2 is not a square of any number. So therefore, this,
Not a square of any number.
I'm sorry? Okay, so in part number C here, so we saw that here, 2 is basically a member of the element, so it's a yes. D here, D is a little tricky here, because if we see here, we don't see 2 as a member of the set, rather we see this here is not basically equals to 2, so both are different things here, so we have to make sure that 2 like this here, it should be like this. This is not 2, so this is a set inside a set. Okay, so therefore the answer is no. Okay, part number E. So part number E is basically it's one set, and inside one set there are 2 sets. Inside the other set there is another set, so 2 and another set of 2. So therefore we know that this 2 is not an element of this set. So therefore E equates to no. Okay.
Why is D no? Why is D no?
D or E?
D.
Right. D is no, because here we cannot see 2 as a part of the set. Here, this set D, right? The members of this sets are 2 sets, right?
Oh, 2 separate sets.
2 separate sets. It's not, so just like I mentioned here.
Oh, can you see it as a subset? A set.
Subsets we will discuss later. Okay, so but at the moment we are saying that 2 is not basically a part of this set, because here this set, the members of this set is 2 sets, which is a set containing 2 and a set of a set containing 2. Okay, so therefore 2 is not a part of this set. And like as for F, we will say no, because 2 is not a member of this set. Any questions?
I didn't quite understand the last 3.
You don't understand last 3?
I didn't quite understand it.
Basically they were asking us if 2 is a
Is
member,
the member of the set.
right? So here, C, we in the part C, we know that 2 is a member of the set, right?
Yes.
Right. So the members of this set C is 2 and this 2, right?
Mm-hmm.
So because this 2 here is a member of the set, so therefore we said yes, this is true, right? In the part number D, let's say, right? In the part number D, the members of the set is a set itself, which contains 2,
Oh, okay.
and then it has another set in which there is another set which contains an element 2. Okay, so therefore, this is not true.
Is it the same reason 9E is wrong?
Exactly, yes. That's the same reason the last 3 are wrong.
Oh, I see.
Okay, thank you. I understand.
Okay. Okay, let's move on to the next one. So here, in order to illustrate the elements of the set, we can draw the Venn diagram for the set. So in this question, we have to draw a Venn diagram. So in the Venn diagram, we illustrate the set of all months of the year whose name does not contain the letter R in the set of the months of the year. So here we will have a Venn diagram. Okay. So here, so this is a set. Let's maybe make a bigger set because we might have to include a very. So this is the set of all months, right? So inside the set, so what we will do is we have to basically to illustrate the set of all months of the years whose name does not contain the letter R in the set of all months of the year. So here, if you will see this statement clearly, so it will say it's first asking us to illustrate the set of all months of the year whose name does not contain the letter R. So let's first make a set, right? So this is the set of all months, right? So all months here will go here, right? And then maybe I can use a circle here. Yeah, that's better. Okay, so I have this once. Actually, yeah. Let's see here. Now we have to list out the month. So this is because the set of all months, so we will list out all the months here. So this is January, this is February, right? So I'm just writing like this. You guys are supposed to write full name, okay? So January, February, March, April, right? Then we have May, then we have June, then we have July, we have August, we have September. It doesn't have to be in an order. It can go any ways because it's a set. October, November, and then we have it December, right? So this is all the months right here. But now we are supposed to which does supposed to illustrate the set which does not contain the letter R. So here, if we will look at these months, so we know that, so these 4 months here, they don't contain the letter R. right? So therefore, this set here is the set of all months. So this is the set of all months of the year, and then this is the set which does not contain the letter R in the set of all months of the year. So it's here in the set of all months of the year. So we have all months set, and then in here we make a subset. So one of you was asking about the subset. So this is basically a subset of the bigger set. Questions?
I get it now. Okay.
Okay, if no question, let's move forward. So next we have question number 23. So basically we have here to find the power set of each of these sets. Power sets are basically all the possible sets, subsets of that set. So let's take this. Okay. So now, so power set, as I was saying, is a subset of all the possible sets. Now, let's take the first part A. In the part A, we have to write the power set. So let's take part A. Maybe I can do it over here. So part A. So our power set is basically a set which contains all the possible subsets for that. So one thing to note here is that empty set, which is, as I mentioned earlier, is denoted by this here, right? So I'm just going to write here empty, but you guys should draw this when during the exams or in your tests. Okay, so empty set is a subset of every set. Okay, so in the power set, this will always be there. Okay, so here we have this set, empty set, and then the other set, which is A itself, the set of A. Okay, so these are the only two sets power sets contain. Okay, let's do for part B. Maybe it makes more sense. So part B here, we will have an empty set. Okay, and then we have a set contains A, set that contains B, set that contains A and B. Okay, so you might have noticed, like as we increase the number of elements in the set, so the power set grows exponentially. Okay, so see here it's a little trickier. So
What about on B? You can't have an empty set and B in one set?
yes, so here in the B part, we have an empty set because empty set is a subset of.
You can have an empty and B in one set, isn't it? Or empty and A in one set.
Oh, that one? You mean like here, this thing?
Yeah.
No, we cannot do this one because then we can make infinite possibilities, right? Because that is not the definition of the power set, because this here is not a subset of this thing, right? Then I can keep on adding empty sets and make it the subset of the bigger set.
Okay.
And then I can just write down until like there are so many of them, like I won't be able to cover. Okay, so the definition of the power set once again is that it's a set of subsets for that element. Okay. So here empty set is basically the subset of every set. So I cannot just add empty and then here, and then maybe I'll be able to add an empty here, and then inside I can add an empty here, right? So there are limitless possibilities, which is not correct. Okay. Okay, so for part C, so we know that empty set is a subset of every set. Then we have this member here, empty, right? So empty, right? And then we have another set here, which contains the set. It's an empty set. Then we have this set itself. Okay, so maybe I can write this one here. So the first element is this set itself, empty set, right? Because empty set is the subset for every set. And then we write this one here, this set over here. One thing to notice is we cannot repeat that. Okay, so therefore we just didn't write it alone. Okay. Then we have this one coming from the second element. Okay, just like we did for this one. Okay. And then lastly, we have the whole set together. Okay, and then this closing bracket over here. Okay. Questions? Okay, if no questions, let's move forward. So this is exercise 2.2. This is exercise 2.2, and it's going to be the last exercise of the tutorial. So we have 2 sets, and then we will be performing the set operations on them. So here, according to the definition, here A be the set of students who live within 1 mile of school, and B be the set of students who walk to classes. So we have this A intersection B, so we have to describe that. So we will say that what's the result of A intersection B? The result of A intersection B will be the set of students who live within 1 mile of school and, right, so this is a keyword here, and walk to classes. Okay. So this is the description for this set. Next, this is called A union B. So we will say this set, the value of the set is the set of students who live within 1 mile of school or walk to classes. It's important to note that or means that they can be both the students who walk to classes or who live within 1 and here who lives within 1 mile of school. Okay, so it basically always the students who satisfy both the criteria. Question?
One question. The U represents union and the opposite U represents intersect, right?
That's right.
Okay.
Okay, so A minus B here, this C part, it means A difference B. So if we have to take the difference of two sets, with this example here, we will describe them as this set of students who live within 1 mile of school but do not walk to classes. Here this but do not, this is the keyword. Okay, so I'm just highlighting the keywords. So this is the A minus B is, so the subtraction of those elements. It doesn't include those elements. Questions? Let's take the last example. So the D is B difference A. Now here we have reversed the order as in C part, but here you will see that unlike the other rules, here the order matters. So here we will say the set of students who walk to classes but live more than 1 mile away from school. Okay, so but live more than, here this is the keyword. Okay? So here once we reverse the order, the members of that set basically change. The order here actually matters a lot. Questions?
Question? Hello? So you're saying that the upside down U is the same as the hand in the shop, upside down V?
I'm saying that this U here
The
is
the same as the opposite upside down V?
it's not
No,
equal
V.
V?
V. Upside down V.
Oh yeah, here this and here.
So that's the same as that.
That's the same as that here.
U. It's the
No.
same as the N, okay, opposite N, okay.
Here, this is not a set notation, right? So this is
Yeah.
not a set notation. These ones are the set notation, right? So if we put these logical operators in the set notation, it won't make any sense. So that's why we have different notations for the logic and for the sets.
Okay, logic is different, okay.
Yeah, logic.
But basically the equivalent, sort of.
Yeah, you can find some sort of an analogy between them, but yeah, so in terms of thinking, yeah, you probably might find it the same. Yeah, but in terms of writing in different aspects, right? So here, this is a different
Yeah,
topic.
okay, thanks.
Okay, let's move on to the next question. So question number 13. So in here, in the question number 13, so we have to prove that second absorption law. So there will be a table in your book. I'm not sure how many of you have it. So, but I will post that to table 1 for you guys. Okay. So here we have to prove the absorption law by showing that if A and B are sets, then A intersection A union B equals to A. So we say we have to use this to solve this. So we suppose X belongs, maybe I can do it over here. So we say X is X, and this symbol here, the backwards E, so it basically means belongs, right? So X belongs to A intersection, right? Or in terms of thinking, you can think it of as this in the logic. Okay. A intersection A union B, A union B. So we assume that X basically belongs to this domain, right? So whatever the elements of this set are, so X is one of the members in this set. Then we know that X belongs to A, and because it's an intersection, right? So X belongs to A, and X belongs to A union B. Okay, just simplifying that equation. Okay, so here this is B intersection, right? So if X belongs to A intersection A unit B, then X belongs to A, and X also belongs to A union B because it's an intersection, right? So this is again by the definition of intersection. And because we know that X belongs to A here, so we have basically shown that the left hand side is a subset of the right hand side, right? In other words, we can say that X basically belongs to A, then by the definition of union, right? By the definition of union, X belongs to A union B as well. Therefore, we can conclude this here, right? So it goes either way, right? So we have prove it going from one way and then the other way as well. So we can basically say this here, because this here, right? X is a member of A, therefore X is a member of A intersection A union B as well. Or we can say because X is a member of A intersection A union B, so therefore X is a member of A as well. Okay, so this is again by using the definition of intersection and union. So this proving the subsets and the supersets. Okay, let's take another question. So we have this question number 21 here. So we have to show that if A and B are sets, then A minus B equals to A intersection B. Here, this B and the line on top of it means that B complement. Okay, so if something is included in B, right? So maybe by diagram I can draw here. So here, let's say this is a set B, right? So inside this set B, there are elements of set B, right? So if I exclude this element B from this universe, let's say this is the universe of all the sets, okay? So any set or any member that's outside of this B here, that is B complement, or B and the line on top. Okay, so here we have to, okay, so let's take part number A. So here we have both side equals the members. X such that, so this straight line here, it means such that X belongs to A and this is and, right? It's a conjunction. And X does not belong to B. So does not belongs, so we'll just put a line across this E upside. Okay, so here, so X is an element in this domain such that X belongs to A and X does not belong to B. This here, this one here, so this is represented in the notation this, right? So this one here represents it. So A minus B can be represented as this. Okay, question. So part number B.
So should we show how to prove that A part actually?
We basically have to, so here we have to show that if A and B are sets, then A minus B equals.
Please, we can't hear you.
You can hear me? Can you guys hear me?
Yeah, I can hear.
Yep.
Is it better?
Yeah, it's fine.
here. Yeah. So someone is asking a question that here that is this a part of showing that proving the statement? Yeah. So basically, yeah. So here we have to write them down in set notation form here. So A and B, we know that they are two sets. So we have to show that this is true or not. Basically, we just use the definition of the difference and the definition of intersection to solve them. And in the next question, we will use the definition of union and intersection to solve these questions and write them out down in the set notation form. Okay, so
Yeah, got it. Thank you.
you're welcome. Okay, so the next part is part number B. So we will say that A here equals A intersection U. Oh, this is a U, okay? This is not a union. So let me just put a little, yeah, A intersection U, right? Which is equals to, so A intersection U is equals to A intersection B union B complement, which is equals to A intersection B, and then let's put a bracket around, union A intersection B complement. Okay, so basically here we started with A, right? We take the intersection of A with some U, right? And then we prove this statement here, right? So we started with the right hand side and then we prove this. And how we prove this? We prove this that A, so any A intersection with U is basically A itself, right? And then we said U, right? So U, we just suppose that U is B union here. So here U basically it means that universal set here. So this is the set of all sets, right? So here this U here basically represents the universal set. So all the possible sets, all the possible elements in the set. So here I have this B, right? So here I have this set B, right? And then here I have the elements other than B is B complement right here, right? So if I take this element B union B complement, right? So this is basically my universal set. So it includes all the elements in this set. Okay, so this is the universal set. Okay, and then this here universal set, I just expand this using the De Morgan's law. Right, so we apply the De Morgan's law on top of it, and it becomes A intersection B union A intersection B complement. So A intersection B, here this one, A intersection B, this union, and then this A intersection B complement here, right? So it's opening up the brackets. Okay, just like we studied for the logic using the De Morgan's law. So we have the same De Morgan's law in set 2. questions? Okay, if no questions, let's take the second last question. Actually, this is the same question. Okay, so let's take the last question. Okay. So here we have to basically draw the Venn diagram. I think this question will give you an even clear understanding of what I mean. Okay, so let me just get these ones. Okay. So we have to draw the Venn diagram for these members of the set. Okay. So here we have this set composition A intersection B minus C. Okay, so we have to draw the Venn diagram. So here we have this maybe I can take shape. This one is good. Okay, so here we have this universal space, and then we will draw A. Let's say this is A, right? Because A is intersected by both B and C, right? And then this B minus C here. So we will show here. So this one here, this represent set A, this here, right? This represents set B, and then this represents set C, right? So first what we have to do is, so B and C, maybe if I can, let's raise this. Okay, so let me just first demonstrate the B minus C. So what are the elements that, so here, let me just take out set A. Okay. So let's say B and C here. So this is my set B. This is my set C. Okay. It doesn't have to be perfectly circle. So B and C, right? So first let's do what B minus C here means. So B minus C here means that the elements that are in B but that are not in C. So all the elements that are, maybe I can show it with the color. Yes, perfect. Okay, so these are the elements that are a part of B minus C, those elements that represent B minus C. So these are here, right? So this represents B minus C. And then we have an intersection A. So let's include A now. Let's use black. Okay. So this here is A, right? And then we have A intersection B. So we have to basically show that A, so we know that this portion here, let me maybe fill it with green. Yes, here. So here, this portion here, it basically represents the members of this set here, because B minus C, it's also there, and A intersection, the elements that are the intersect of A and B minus C are also here. So this section here represents this. Okay. So the elements of this sets are in this intersection part. Questions? Okay. Okay, if no questions, let's take another example. Part number, let's do part number C. See here. So we have A intersection and then we have B complement. We have the brackets around. We have union. We have A intersection C complement. Okay. Okay, let's take a universal space. Should be okay. Okay, so we have A intersection with B complement and C complement right here. So let's say make this A. Let's try to do this part, A intersection B complement first. Okay, so this is our set A. Let's actually make this over here so that we have more space. Okay, so A, and then this part here, B. Okay, so now we have to basically determine what A intersection B complement is. So if I have to represent the space B complement, maybe I can fill that by color. Right. So this is, so right now, whatever you see, the colored part is the B intersection space, or B complement space, I mean. right? And then we know that A intersection, so the space that intersect with the part of A is basically A intersection B complement, right? So maybe we can use this color to fill this. So this space here represents the element of this part here, A intersection B complement. So the members in this part are the representation of this notation. Okay. Now let's solve this A intersection C complement. So here, let's include C in the shapes as well. Let's use black. So we have this as C. Okay. So now we have this A and then we have C. So now if I have to represent C complement, so that is everything outside of this circle, right? Everything outside of this circle, C, right? And then anything with the intersection with A, so which will be this part, and including this part. Including this part, right? And excluding this part. Okay, so this here represent A intersection C complement, right? And from before, we don't have this part included. So we know that the union of this part here, and then we had this part, and then we have this part and this part from A intersection C complement and A intersection B complement. So this shaded area, which is represented by these two here, the pink color, right? Or more like a purple color. So they are basically the representation of the elements in this set. Any questions? Any question, guys?
No, it's fair enough.
Okay, yeah, so basically I think this will make more sense if you guys try on your own. And if you guys have any question, just write me an email, or you can also ask me to solve them during the tutorial, but just leave me an email almost like 2 hours before, so that I have enough time to prepare for those questions. And yeah, if you guys don't have any questions, then I will see you guys in the next tutorial. And I will be uploading this tutorial and the notes on Moodle and the Microsoft Streams for the tutorial. So if you have any doubts, just ask me in the next tutorial, or you can also leave me an email. So that's pretty much it for this tutorial, guys. And I will see you guys in the next tutorial. Okay.
Hi, sir.
All right, thank you.
Bye, guys.
Bye, man.
Thank you.
Bye. Bye.
Thanks, man.
Bye. Bye.